Hi, I'm Stephen Forrester. I'm the principal engineer of DMA Engineering here in Golden, Colorado. Um, I have a master's degree in mechanical engineering, and way back when I did my master's report using a homegrown CFD program using C++ back in the day. Things weren't as sophisticated as the tools we have now, which is exciting. We can do a lot more with it. So this is our presentation on improved restaurant air quality with corresponding energy efficiency gains. So the objective is to better understand what can we do with the current HVAC systems and mixed air conditions. What can we do differently with that to make the restaurant a safer place for people to hang out at? And then two, how can we couple the back of the house with the front of the house and get energy savings there? So that was our approach. So here in Colorado, there was extensive efforts made to make restaurants safe. The Colorado Governor's Energy Office, or the Colorado Governor's Office here, came up with this 5-star program. We were working with them through the Colorado Restaurant Association to add ventilation to it, to increase the ventilation with it. The Wells-Riley's equation says that the longer you're in a space, the more contaminant, the more chances of you being getting sick increase with that. And then also there was that restaurant in China that they came out and they said that people got infected with COVID through the HVAC system there. There was a CFD model done a while back on that kind of showed how that happened. Somebody sneezed and how it spread across the people at the table there and moved across to a couple other tables there due to poor just strategy and how being in a restaurant with that happens being unmasked. So again, HVAC focuses on contagion, dilution, and filtration. The latest ASHRAE journal that just came out, I believe it's the November one, came out, and it says, that they talked about portable air filtration. We looked at that for a couple of restaurants here as well. But again, filtration, can the equipment handle additional filtration? Is the equipment is size big enough? Is the pressure drop going to reduce airflow? Are you going to end up freezing coils? What's going to happen there? How much air can we actually bring in through the unit without degrading performance of the unit? With size for one outside air, now we're asking it to bring in more. The mixed condition can be higher. So several things that can go on there that can make it make problems with it. So the objective. So what can we do to mitigate the potential for cross-contamination as a result of current HVAC mixing? So our approach was to create a CFD model of several different ways of doing it: mixed flow, displacement ventilation, radiant sealing, and then displacement ventilation combined with radiant. And our radiant, we used mixed conditions with it as well. We started out using open foam as the CFD engine. For those that know how to use open foam, you really got to be underneath the hood a lot with open foam to get a lot of what you want out of it. We changed over to SimScale. There were some issues with SimScale that ultimately led us to use the SolidWorks flow simulation, was the tool that we used to do the bulk of our simulation. So we modeled a typical restaurant that we designed several years ago. We just did the dining room, modeled that with the CFD, just pretty basic restaurant area, 62 occupants in it. Just a standard mixed air condition, pretty basic. So the boundary conditions for this, we used the cooling supply was 2,601 CFM at a 55 air inlet. And then the heating was 1,197 at 110 degree in-layering or supply air temperature, sorry. The load of each patron was 250 BTUs per hour. One exterior wall that had glazing on it, another exterior wall, and then another exterior wall, and then the back wall was up against the kitchen. So we just applied a boundary condition there of a temperature on that one. So then we generate, the standard outputs out of a CFD model, the velocity contour plots, the temperature contour plots, the system velocity streamlines. we use those to qualitatively understand that the model was producing results that was accurate. We did this for each and every single case. The main parameter that we were looking at was the PMB relative comfort plots to make sure that the PMB stayed within, not greater than 1 and not less than -1. So that was where we were bounding all the simulations to make sure they were accurate to that. So then we did displacement, ventilation, boundary conditions, and initial conditions. The CFM was 1,930 for both cooling and heating. The inlet temperature was 63 and for cooling and 76 for heating, so very low. That's the advantage of displacement ventilation. One thing that was interesting, we were looking at this as a retrofit, and with that being the case, where we actually put in the diffusers was not ideal. So we had to work with one of the manufacturers to figure out exactly where we could put these air inlets. This one back here was actually sized to be taller. We made this back wall a little longer, and then we rotated it 90 degrees to put more airflow closer to the ground. Kept the same returns up high. I think there's a lot of optimization that can be done to strategically push the returns. We did not take it that far. We just kind of added the 2 from the mix and then added another one to help out, or another 2 rather to help it out. Yeah, and the other thing that's interesting with the supply air temperatures, the energy model that we were using kicked out a number that we didn't feel was accurate. We went back to the manufacturer and they came back with something that was a little bit closer, and that allowed us to start iteration to figure out exactly what the supply air needed to be. Again, we were using the PMB to figure it out. Then we did mixed radiant with mixed. So we did mixed airflow with radiant sealing on this to figure out what that looked like. The total airflow rate was 684 CFM, 68 inlet, 78. So pretty close to the neutral temperatures of the space with those. And then the minimum CFM was just based upon ASHRAE 62.1. The radiant temperature was 52.5 and 110 degrees. So that a little bit different. We did add in an air inlet right here in the front to be more of a linear slot. And then we put in the pressure return outlets in the back. That just kind of simple again, right? I think there's definitely some optimization that can be here, but the exterior boundary conditions on the surfaces was the same. So that no change there. And then we did displacement ventilation with the radiant as well. And I didn't mention this on the other slide, but when we went to one of the manufacturers and started getting information that we needed on the radiant panels, it was pretty close to be that we needed the whole ceiling to be there. So we just assumed in the model that the whole ceiling was a radiant ceiling panel and went with that. And that's kind of the boundary condition that we use there. And then the displacement ventilation, we used the exact same layout with the diffusers that we used in the other one. And then we just put a supply air boundary conditions on that with 665 and 76. I think there, again, we could have done some optimization, got rid of a couple of these, but we felt that this gave a good, representation of getting air, good quality air into the space based upon these locations. They could have been made smaller, a little bit faster velocity. I think there's probably optimization that can be done there. We did not take it that far. Radiant temperature, again, 52.5 and 110, and then the 65 and 76 for the supply air condition, kind of keeping everything there. Those numbers were based upon the, doing a little bit of iteration to figure out exactly where it needed to be. So what we were really after with this study was in the breathing zone at 6 feet, as defined by ASHRAE 55, and then 50 feet per minute maximum velocity, again by ASHRAE 55 for comfort. What does the horizontal velocity look like in the space up to that point? And then what does it look like with the vertical component with it? So what we have is the black lines are just going to be the horizontal velocities, and then we add in the vertical component, and that's the red line. So if the increase in velocity with the red line is there, we're like, okay, well, it's going more in the vertical component, so that's fine, right? That's what we want. It's whisking contaminants away. And we just took one probe point right in the middle of the space, and that's where we made our comparison. You could go through it ad nauseum where you're going to put these and figure it out. And I'll talk about a little bit about that in the closing part of it and the challenges that we came up with. But from this, here's the mixed flow condition. It's a lot in the horizontal condition. There's a little bit of vertical component at the lower. at the lower height. And then as we get up to like 4 feet, it becomes all together. Displacement ventilation, kind of the same thing, but it's kind of the opposite, right? It separates, they're closer together at the floor. And then as it goes up, it becomes more vertical than it does the horizontal velocity. So from about 3 feet to 4 feet, not a lot of velocity there. And then, 5 to 6, it goes up. Mixed radiant didn't turn out as well as I thought it would. But the reason is that when we have the radiant ceiling, right, you get cold air that's falling and you get the air from the ceiling that's all falling, you get buoyancy effects going on in the space. And that's what's causing this velocity increase. I think if you were to do a radiant floor, there could be some stuff that could happen with that. We did not model it because we were looking at this as a retrofit application, so that we didn't model that. And then displacement ventilation with the radiant actually helps out those buoyancy currents and kind of gets them to straighten out a little bit, if you can see by this one. And again, this is all the cooling plots here. So then we do the same thing for the heating plots. Mixed looks pretty good as far as just, the horizontal component stays about 10 feet. It's pretty close to what it is for the displacement ventilation. Displacement's definitely proven to be better. Mixed radiant definitely looks a lot better than it did with the cooling application. And then displacement ventilation with radiant, again, looks really, really good. So taking it together and just comparing the displacement ventilation against the mixed, because the displacement ventilation definitely proved to be the best between heating and cooling. So we could just do a comparative now between the cooling and heating of displacement ventilation versus mixed. And these are the results here. And with that, the dashed lines represent the mixed, the displacement ventilation, and the solid lines are the mixed. And you can see that in the cooling, definitely the displacement ventilation has less horizontal component up to the 6 foot height. So that's, it's looking pretty good there. The vertical component is definitely showing that we are taking contaminants away. Heating comparison, it's a little bit of a mixed bag here, all the way up to about, 1 foot to about that 3 to 4 foot. Displacement ventilation is performing about the same, and then 4 to 6 feet. They're both performing, adequately. The displacement ventilation kicks up a little bit. If you think about where we're at in a restaurant, sitting, your head height's going to be right about that 4 foot, the 3 to 4 foot range is where your head's going to be at. So, having a less contamination in that area is going to be important in that. It's interesting to note that all the velocities are pretty low, right in this zone. And we'll talk about that a little bit in the conclusions about, that low velocity and what the implications of that are. So then we took it one step further and we added in a contaminated person coughing, 2 people coughing at a table or speaking at a table with the mixed flow design, and just to see what that was and see what the particle trace looked like. When we did this, there was a couple things that came out of this quickly. We had to add a lot of mesh right around the mouths of people. So that took a lot of computational time to do it. The way SolidWorks does it is you solve the flow, you solve the whole flow field, and then you add in the contaminant trace as a post-processor. And that's what we did here. We used hot air at a certain micron for what, an exhaled hair would be, and created this plume and looked what it looked like. The interesting thing is, it's like you can do this with 62 people in a space. Where do you put the, the contaminated person? What does that look like? I think you can keep doing this to ad nauseum, and I just don't know what you're going to get. I think using the vertical, horizontal traces in the vertical plane and understanding what that looks like, and then using some empirical data that's out there and say, well, what does it actually look like if somebody's contaminated in this area? It's easier to go through and put probe points and look at that, and then, get a sense of what the empirical is. So I don't think going through and doing this study for a whole entire restaurant is actually practical. And that's why we didn't do more than just a mixed flow design. It's just very computational. It takes a lot of hours to do it. And what are you going to gain? I mean, we don't exactly know where the sick person is going to be. You can only do what you can do. So you got to make a judgment call at some point. So then we looked at the energy modeling part, and we're like, cool, all right, we kind of figured out a way that we can reduce the cross contamination in a space, but now how do we make it pay for itself? Electric heating is coming along. Denver wants everybody to be electric heating by 2030. So how do we do that in a restaurant? We looked at it as there's opportunities that exist where the dining room's being cooled, and then we're making domestic hot water in the back for cleaning. There's a lot heat generated in the back. Is there a way that we can make like a central plant, scavenge heat from one one component to the other and reject heat back and forth. And we created this energy model with Design Builder using the Energy Plus engine. One thing for us, there was a lot to consider on how to do this. We had to write some custom scripts, work with the folks at Design Builder to get a custom scripts written. How do we reject heat from this condenser to a district heating plant? And then also this here is representing the walk-in cooler, reject that heat to this district heating plant and then put it back into this domestic hot water plant. What does all that look like? It was some challenges to get that to all work out. This model that we have shown here is for the radiant heating and cooling, and that's what's being shown down there in that block. But as we go to this slide, we can actually see that there was actually energy savings here. The one thing we did is we made the gas range constant through all the models. We didn't make that into an electric range using, like an induction range or anything like that. We kept that all gas just for the simplification of it. So that's what you're seeing down here is that the differences between the mixed had gas heating and then displacement ventilation and radiant had electric heating. And that's the balance there is the range that's being there. Looking at it, the displacement ventilation actually has less utility cost. And that's a lot to do with that lower supply air temperature. Displacement ventilation or the radiant has, we were 52.5 for the radiant cooling, and then we were at 110 for the heating. So there's energy there. Things aren't running as efficient as it is with the displacement ventilation. So we're getting some energy savings there. It's not a huge amount of energy savings, but it is. If you're concerned about annual CO2 equivalent reduction by design, we at DMA Engineering care about that type of stuff. So this is what it looks like there. There is definitely the displacement ventilation is the best, and then radiant's the second, and mixed is the worst. And then the annual electricity by design type, if you're looking to offset your energy consumption, as we're trying to get to net zero and decarbonization of the grid, these things are important. So, the displacement ventilation gets you there quicker. You don't have to buy as much solar or offsets or what have you. Radiant, again, is the second best, and then the mixed is the third. So challenges. We designed this model as a retrofit. I don't think if you were to go through and do displacement ventilation or radiant technologies in a space, you could do it in a retrofit application. Too many challenges to actually get the diffusers to line up correctly. Your best beat is just to start over with a clean sheet of paper. And that would have made it a lot easier. And then the other thing to note is that the velocities we were talking about are very small. So in a fast food or fast casual, people are going to be coming in and out and moving through the space a lot. And they're going to be disturbing the air, and in the HVAC scheme is not going to help in that instance. So we're looking for more of that contemporary to casual dining, where people are actually going to be sitting from an hour to 3 to maybe 4 hours in a space. The weight people are not going to be walking by as much. They're not going to be disturbing that air. And then it comes back to the Wells-Riley equation. The longer you spend in the space, the more chances of you getting infected if there is somebody infected in the space. So considerations to transition to these designs. There's a higher upfront capital cost with both the displacement ventilation and the radiant. A retrofit is extensive. And then contractors, we're all fighting shortages right now with the qualified contractors. Every contractor knows how to go out there and do mixed type system. So it's pretty easy to find there. But the selling points are there's improved occupant comfort, reduced risk of cross-contamination, reduced energy consumption because there is energy savings. If there's PACE equity financing going on in your area and it's owner occupied, you can get financing done because there is energy savings. And then, just the marketing advantage of being able to say, hey, we've gone that extra step. We've done everything we can to, reduce the contamination in our space. We're trying everything we can. So lessons learned. If we were to do it over again, probably would have just taken a generic restaurant and try to find as much symmetry as we can to speed up the results. Symmetry is going to make things a lot easier. We just used the state, a restaurant we had, we were like, can we look at this and make it as into a retrofit? But computationally, there was a lot of time with that. And then where are you going to put your probe locations? What data is important to you? Where are you going to look through? Model setups are always difficult to do. It takes a while to get a good model set up and make sure it's running. So that was there. And then the advanced energy modeling. The scripts definitely was something that we had to deal with, and it took us a little bit of time to figure it out and how to get the scripts to work as they were. and so once we got over that hurdle, it worked really well. But Energy Plus made an update, and we just reran the model to look at some data the other day. And there's some naming conventions that changed. We had to go back and rename some stuff in our scripts to get it to work again. So, I mean, it's just when you're working outside of what's the common blocks within the software, you just got to, there's some challenges there. Particle trace, again, I think it's a great tool, but I don't know how practical it is to use in every application. I think there's just too many variables in there to figure out exactly how to make it all work. So again, I think it's good to try to get some base data to maybe to get an insight, but to actually model everything that can be modeled, I don't think it's practical. And then I just really want to reach out to the team at DMA Engineering that helped us out, Paul Chachedo and Angelina Caliende. They did a lot of the energy modeling. Paul helped out with some of the CFD work when we were using OpenFOAM and SimScale. Byron Guerrero stepped in and helped us out when we were using the SolidWorks flow simulation, really got that taken care of. And then Michael and Danielle really helped out in getting this presentation together. I'm really here just presenting. So really thanks for your time, and I hope you got some valuable information out of it.